Hello everyone, welcome to lecture 4.1, which is on curve fitting. Unit 4 is going to be looking at basically developing models for data that's collected experimentally and how to also interpolate between points from experimental data and tables. So we're going to look at a bunch of interpolation methods. And then this subject is basically related to also kind of image processing, where we try to smoothen the colors within an image to reduce kind of that pixel look in an image. So all of this together is, kind of related to data collection, and an image could be considered a data collected kind of data set, and processing that data. The first thing we're going to look at is how to basically fit a curve to a set of data points. So typically data points, when we collect them, they're going to be in the format, if we collect kind of a 2D type of data where we have only x and y, the data is going to look like x1, y1 as a single point, and then x2, y2 as another point, and so on until you reach to xn, yn, where n is the number of points that we have in the data set. So typically on a graph, if we kind of did an experiment and we wanted to graph the data, we would get something as we see here, kind of points with some type of trend, which we can use that trend to figure out what is the type of model that would best fit the data that we have. So looking at the data that we see here, we can kind of say, well, you know what, if I draw a straight line through these data points, then it might actually fit the data that we have. So we can try a straight line. And again, usually you would, right now I'm doing a random straight line, and typically in a computer you would fit the data using some type of algorithm and then draw the line that best fits the data, and not just manually drawing a line as we see here. And we'll look at the algorithm that is used to actually make such a point or such a line. So this line has a standard kind of format of or equation of ax equal plus b. So typically, maybe in high school, you were maybe used to the format of mx plus b. And in this case, the a is the slope and then b is the intercept. So when we look here, we're trying to find the line that best fits, this data points. How do we judge, how well does this kind of line fit the data? Well, we look at the error that we have, between the line and the points at a specific kind of x mark. So as example here, we see that this green line here, the amount of error between the straight line and the data that we have. Another point here, we can see this would be the error. Again here, this would be the error. This one could be a bit larger, and so on. And some of them are smaller, some of them are larger, as we see here. So all of these dotted lines are basically straight lines going parallel to the y-axis, and they show the error that we have between the line of best fit that we just drew and the points that we have. And obviously the line doesn't go through all the points as we see here, or also as well, it doesn't actually go through any of the points, but it tries to fit the data as much as we can. So the way to judge if a line fits the data well, we're going to have to look at the error. And there are different types of error. So let's highlight the different types of error and how we can use them to basically determine what is the line of best fit. All right, so the first type of error is basically called max error. So these are the errors, and the first one here is the max error. And from the name you can see that it's essentially what is the maximum error that we get between the line that we drew and the data points that we have. So to find this, we would have to check all of the values of the absolute values of the errors that we drew kind of in green here. And the way to do that is in terms of an equation is f of x, where f of x is basically the function that we have here. and comparing this function with the values that we have in the y. F of x is y in a way, so we would compare that with the y of every point that we have. And the maximum error that we got would be considered the max error. So in a way, this doesn't really characterize the full picture of how well does a straight line kind of fit the data, but it shows us at least what is the maximum kind of error in the line that we have. And obviously k here would be represented by integers, where we go from 1 to basically n number of points, however number of points we have in the data set that we have. All right, so the second type of error is called the average error. So let's draw the average error. So the average error is represented by the equation E1 f equals to 1 over n, which is basically dividing by the number of points, times the sum of all of the errors that we have in the graph. So in that terms, that would be basically f of x, which is the point or the value we get from the straight line or the line of best fit, minus the actual values that we got experimentally for all the points. So this would be the average error. The third type of error is called the root mean square error. So root mean square error. And in short, it's called RMS. Now, this is the most commonly used in practice. And what we'll see is actually, in fact, this actual type of error is used to derive the line of best fit. So here we have the most commonly used in practice. And the equation for that is e2 to the f as a function of f, and it's equal to square root of 1 over n, which is the total number of points, times the sum of the errors. But in this case, instead of just the sum of the errors, we're doing the square of the errors. So we have f of xk minus yk, and all of this together is squared. So without the absolute here, because the square itself, if it's a negative, it will become a positive anyway. And what this does is it squares the distance, and because it does that, whenever we have a large error or a point which is really far away from the actual best line of best fit, then we have more weight when we use this method. So it squares the distance between, or because it does that, therefore, hence points that are far from the line of best fit have a significant effect on the value of the error. So the next thing we're going to look at is how do we in fact find the line of best fit using the RMS. So how do we find the best fit? And obviously the goal here is to minimize the error that we get with the line of best fit. So goal is to minimize the error. And for our RMS, for the equation basically of the root mean square error, the main part that we need to minimize is essentially the part which is inside the square root, which is the sum of the errors squared. So main part to minimize is the sum of the values of the function subtracted by the experimental values squared. This here is basically called sum of the squares of the residual. In short, SR. For a linear fit, right, what we have here, we can plug into this equation what is actually f of x which is basically kind of the linear line equation. So for a linear fit, what we have is the sum of a constant a times xk, which is the value of x where we're finding the y, plus b, where b is the y-intercept. So this here, essentially is the linear line equation. And from there, we subtract the experimental values, right? And we square this. And again, this is sum of the squares of the residual, so SR. How do we solve for the minimum of a function, such as the following? So typically in calculus, what we did, we kind of looked at graphs in calculus and then analyzed them and found out, what is the best way of finding the minimum. So let's graph this first. So if graphed, we might get something like this. So obviously this would be a function of a and b because we have two constants and we're changing these constants. And we can probably get a graph that kind of looks like this, where we have a minimum, and this minimum is kind of our goal that we want to get to. So the goal is to get to this minimum. So typically in calculus, like I mentioned, the best way to find a minimum of a graph is to find where the derivative is equal to 0, right? Because when the derivative is equal to 0, the slope here would be 0, and that would be our minimum. So when derivative is equal to 0, we find the minimum. So we have an equation here. This is the equation. So we want to find the derivative of this equation in terms of, say, example A, and in terms of B, and then find out what is the minimum, or where does these kind of two equations give us a value which is a 0. So let's do one by one. So in terms of A, we have the function, right, the RMS function, partial derivative in terms of A is going to equal to the sum of 2 times A xk plus b minus yk times xk. And we want to set this to 0 because that is where we find the minimum. To simplify this equation that we see here, so let's simplify this. What we're going to get is the following. And we can rearrange it in a way so we can make it look like a set of linear equations to solve afterwards. So let's rearrange this again. So let's call this equation A. And now we're going to do in terms of B. So again, we do the partial derivative as we did here in terms of A. Now we're going to do it in terms of B. And then again, we rearrange to make it look like how we would kind of take an advantage of an equation so we can solve it in a set of linear equations. And this b times n here basically comes from the sum of b n times, which is n number of times, essentially, which is basically equal to b times n. So let's call this equation B. And now basically what we have is two equations with two unknowns. So basically it's a linear set of equations and we can follow the format of AX equals B. So you guys don't have to worry about deriving all these things. So right now I'm just kind of showing you, we started off with the line of best fit for a set of data points. Then we looked at the error, and then we're using the error to find the minimum, which is the RMS error, and finding the minimum of basically the sum of the squares of the residual for the equation SR. And from there, we took the partial derivatives, and then we're going to solve it. But at the end of the day, we're going to get equations that you will use to basically find the lines of best fit if given a set of linear data points. So in terms of matrix form, where we have a coefficient matrix, and then we have a vector x and a vector b, as we look at the equations here, equations A and B are actually the unknowns, so we're going to have those as the vector of x, and then their coefficients would be what we see in this equation. All right, so let's put these in. So we have n sum of xk, and what we're doing here is we're basically putting equation B first and then equation A afterwards. And we're flipping the order of A and B. So we have B first and then A, and then what these are equal to for equation B is the sum of yk, and then for equation A, it would be the sum of yk times xk. So on this left side, we would put the coefficients from equation A. So this approach essentially is called least squares fit. And basically solving for A using Kramer's rule, we get the following equation. And the important thing here to note is whenever we have the sum of x times k, you have to do x times k for all of the points first and then take the sum. And whenever we have, in this example, the sum of xk all together squared, you first do this part and then you square it afterwards. And this part, on the other hand, you have to square all the values of x first and then take the sum of those. So from equation B, since we solve for A, we can plug in A to equation B and solve for B, and what we would get is the following. To simplify this further, what we see here is 1 over n, which is the number of points, times the sum of the values of y. This here essentially is taking the average of the y values, and this here is also taking the average of the x values. And in short, this is represented by this symbol here, where we have a y with a bar on top, and this here is represented also by an x with a bar on top. So what we get in here in this case is y bar, which is the average of y, minus a times x, which is the average or the mean of x. So now once we've done this line of best fit, we came up with a line and we're all good. Now what we want to do is check how good is the fit, right? What is the goodness of the fit for the lines that we have come up with using this least squares method? So we have different kind of equations. So the first one that you're probably most familiar with is the r squared. Whenever you plot in Excel, you get a line and you fit the line to a kind of a straight line or any type of polynomial. You usually also can ask Excel to display the r squared value. And from that, if the r squared value is close to 1, you know that you have a pretty good fit. And if it's not close to 1, it's much lower than 1, then you know maybe the model does not fit your data very well, or your data has a lot of basically errors or noise within the data. So that r squared is called the coefficient of determination, which is r squared equals st minus sr divided by st. Sr is the sum of the squares of the residuals around the regression line. And then st is basically the sum of the squares around the mean. So let's write those as well. So we have st equals the sum of the values, yk, which is all the points that we get from the data, minus the average of all the points squared. So this here is called the sum of the squares around the mean. And then the second one here, SR, which we've seen already before, is all the values, the points yk minus b minus a x, and then all of that squared. So essentially what we have here is kind of the equation of the line of best fit, and then what we have here is the points. So, and also the line of the best fit is also called the regression line. Another way of writing this is also in terms of the coefficients a0 and a1 instead of b and a. So we can write the sum as follows. And again, to note, this is called the sum of the squares of the residuals around the regression line. So for a perfect fit, right, SR would have a value of 0. And if SR is 0, if you look back at the equation here, we would have essentially ST minus 0 divided by ST. So then ST and ST cancel out, and essentially what we get is R squared would be equal to 1. So that means the line of best fit fits the lines perfectly. On the other hand, if R squared equals 0, right, then that means ST and SR are equal, and that means the mean is the same as the linear fit line. Other useful statistical kind of values is the standard deviation of the points that we have, and also the variance, and also the coefficient of variation. So let's write all these down as well. So the first one is the standard of deviation, which is the square root of ST divided by n minus 1. Then the variance is SY squared. So whatever we see, the standard deviation basically squared. And then the coefficient of variation is CV equals SY divided by the average Y value times 100%. So that is our first lecture on Unit 4. And essentially what we've seen is how to fit a line into a set of data points, and how do we look at the error, and we looked at the RMS, and how can we use the RMS to minimize the error to kind of get the best values for the coefficients A and B, which is the slope and the kind of y-intercept. And then from there we took the derivative, found kind of an equation to find A, which is this equation here, and then an equation to find B once we found A. And then after that, we looked at some statistical kind of equations to analyze, how good is our fit. And also after that, these other kind of equations for kind of characterizing the data points that we have in terms of their standard deviation, their variance, and also the coefficient of variation. And all of these do not rely on the actual lines of best fit, but they basically analyze kind of the data set that we have. In the next lecture, we're going to look at how to fit polynomials, and also how to start doing interpolation using Newton's method.